Hello everyone. In today's video, we are going to perform three major activities. The first thing is that we are going to compare four different activation functions. And then we'll evaluate their accuracy and training behavior. Then after that, we'll predict the probability of default for a new borrower. And with all this, we'll use the German credit data. Now, before we delve into the codes, I'm sure someone may be asking, what is an activation function? So let's just briefly look at what an activation function is. So when we talk about an activation function is a mathematical function that is used in neural networks to determine the output of a neuron based on its input. Now, bear in mind that activation functions are very important because they introduce nonlinearity into the model in order to be able to learn the complex relationships among the different variables that we have. So, because of this, the activation function decides whether a neuron should be activated or not. And it does that by calculating the weighted sum of all your inputs and also adds a bias term. So the end goal is that the bias term should be reduced. So let's look at this typical example in terms of an activation function. So in this example, we have just three features or three variables, x1, x2, and x3. So the weights are initialized over here, and there are set by which the weights can be initialized. The popular way is just by randomization. Some others would also use zero weights as their initial weight. Now, when the weights are initialized here, then Z here is computed by multiplying each input with its respective weight and summed over the number of inputs that you have. In our case, it's 3. And then B here is your bias component. So then it means this becomes a function, which is an activation function. Now, this function helps us to get a predicted output, which is then compared with our actual output. So then a back propagation can now be used to be able to adjust our weights. So this is generally how an activation function works. Now, activation functions come in different forms, as I mentioned earlier on the script. So let's go to the script and let's use the four major activation functions to be able to evaluate the probability of default. So in order for us to write our script, we should be wary of the libraries that we need. So over here, the libraries I call in here are the libraries to help me with data manipulation. And then my machine learning library can also be found here. And then line 18 here is the library that I use to visualize my observations. Then over here, what I do is I also call in my deep learning libraries, which include my TensorFlow, Keras. And then over here, I'm able to save my model or save my encoders. So let me make sure I have run these. Okay, so no errors so far. So then, of course, my first step is that I'll call in the German credit data set. Now, this is where I have the German credit set on my computer. So I call it in and I just call it as a path. Then now I come here and then I read that data which I have called in as a path. And then I now call that one Kwame. So I sit here and I think we are doing good so far. So what I'm seeing here is that I have 1,000 observations and I have 14 variables in there. And because my target variable to be status, because I know the data set very well. So I just run that and say my target variable is status. Just in case you didn't know the data you were working with, or you were not sure about how your import of data went, you can print this and then look at the data loading or data import, and then you can also look at the shape, so that instead of looking at 1,000 observations, which I did up there, and 14 variables, you can do that. Then you can look at the variables you have in there. So when I do that, everything I have looked at here is showing here. So I see that, oh, okay, it has 1,000 observations, it has 14 variables, and these are the titles of the columns there. So this is where my status is. So now that I know that, it means I can create the features, and then I can also encode my categorical variables. That is what I do here now. Now, one thing I forgot to mention is that I set my seed here to ensure that the model I'm going to run is going to be reproducible. So that is why I set this. You can choose any number you want to set the seed. So I just have to be sure I had run my seed, and I think I didn't run my seed. So in order to have reproducibility, I'll just go back and then run my seed and then do everything again. So I have my seed run. Good. So now what I'm going to do is I'm going to split my data set into feature variables and target variable. So everything but my target column is going to be my feature variable, and then my Y variable is going to be my target column. Then following that, what I'm going to do is I'm going to make sure I encode my variables. So I'm going to convert variables that are needed from strings to numbers. So that is what I do over here. And then once I'm done, what is I'll save. And so these are for the features, and then these are for the target variable. Then what I'll do, make sure I save them using my pickle, so that anytime I want to reuse them for predictions, I can always do that. So then I'll run this, and then I see how it looks like. Okay. So then in the next step, this is when I utilize my machine learning libraries. So for me to utilize my machine learning libraries, what I do is I want to split my data into training and testing data sets. And of course, you are aware that we run our model on the training data set, and we test the accuracy of our model on our testing data. Of course, some would test it on their training data, but we know that when we test it on our training data, it gives us a false sense of confidence, because most often the model has seen the training data already. So it is easily able to predict than data it hasn't seen. So in this step, that is what we are doing here. So what I did is I arbitrarily chose just 20% for my split. And then what I do here is I bring in the stratify, because don't forget my Y is a binomial distribution. So what I'm trying to do is I'm trying to make sure the ordering is maintained over here. So that is why, or preserved over here. So that is why I bring that. So I do that here. And then the next thing is I make sure I am scaling my variables. Now, scaling is important because we don't want to, at times you may have some feature variables, and some of the feature variables may be large whilst others may be small. So we don't want a situation whereby unnecessary weights or unnecessarily large weights will be attached to features that may be large. And then when it comes to penalization, times you don't want variables that are very small in terms of their size to be penalized. So that is why we scale. So what we scale into is we transform or scale it into a standardized normal distribution whereby the mean is 0, standard deviation is 1. So that is what we do over here. So I do that here. So once I did the training, because I did an 80% and 20% split. So I'm seeing my training set here is 800 observations, and my testing set here is 200 observations. And take note that this is for the feature variables. So the feature variables, I have 13 variables. Then now, this is the time I can build my activation function or my neural network, I should say. So over here, I'm building my function. So to build my function, I need to specify what I want for my function. So I my input, and then I first bring a standard fully connected set of layers. So I begin with my hidden input, and my hidden input, I arbitrarily chose 64 neurons. So that is what I chose. And then for the purpose of regularization, I also select dropout rate of 30%. So that what the dropout rate does for me is that it helps me to prevent overfitting of the model. So at any particular point in time, the model will drop out 30% of my observations. So I have my input layer here as 64. Then I come, and then this is my hidden layer. My hidden layer is 32 neurons. And then it is with my hidden layer that I want to compare my activation functions. So I have that showing here where I'm comparing my activation functions in the hidden layer. Now with my output layer, I'm using just one neuron, and then I'm using a sigmoid activation function. Now the sigmoid activation function is being used because my data is a binary data. It's either it's a 0 or a 1, because in the target variable, the status, it is either a bad credit or a good credit. Now, because of that, I want my probability to be between 0 and 1. So it is the sigmoid activation function that allows you to have a probability or an outcome or prediction to be between 0 and 1. So that is what I have here. So over here, we don't have an option, and we are not trying to compare different activation functions because they have different features. Then apart from that, the optimizer, typically most people will use the Adam optimizer. So I just use an Adam optimizer for this. And then the binary cross entropy is my loss function, and this is a suitable loss function because we are dealing with classification outcome. And then I bring in the accuracies. So with that being said, I can run this model here. So I have run the model. So now I introduce the activation functions that I want to compare. And the activation functions I'm trying to compare are the rectified linear unit activation function, the sigmoid activation function, the hyperbolic tangent activation function, and then the exponential linear unit activation function. So with that, it means I have to create a loop so that each of these activation functions would be evaluated on the same data, and then we can see its accuracy. So that's why I create the loop. Then what I do here is that I also set in a validation split from my training data set. So what I decide here is that 20% of my activation data set should be used for validation of the before it is tested on the testing data. And then I set an epoch or the number of epochs to be 20, in that the model should go through the sequence 20 times. And then what I also do here is that I set a batch size of 32 observations per run. Then I just chose variables here so that it doesn't show output whilst running. Then after that, I indicate that when there is a prediction or predicted probability of greater than 5, it be my bad credit, and then less than 0.5 my good credit, just as it is in my data set. So with that being said, I can run the model and then plot some visualization to see how my model looks like. Okay, so we have our model running here. Okay, so this looks interesting, right? So of essence to us is our accuracy. So based on this data, what we find here is that the rectified linear unit had an accuracy of 0.745. The sigmoid function had an accuracy of 0.77. The hyperbolic tangent had an accuracy of 0.755. And then the exponential linear unit had an accuracy of 0.755. So the sigmoid activation function is the clear winner for our hidden layer because it had the highest activation function. There are some other metrics that you would also see here, and you can delve into them if you want. But we can also look at the plots here. So we see our prediction accuracy for the exponential unit, exponential linear unit. We are seeing the training accuracy and the validation accuracy, and then we're also seeing its loss here. Of course, we all want the loss to decline, so we are seeing after a different number of epochs, we set our epochs at 20, right? So after this different number of epochs, we are seeing a decline for both of them. And then this is the measure of the accuracy, this is the measure of the loss. So this for exponential linear unit. We could look at the hyperbolic tangent also here, the 6 here. We could look at the sigmoid also here. And then we could also look at the rectified linear unit here. So now we know that our sigmoid function performed better. Now, since the data is a credit data, what we want to do is, assuming a new borrower comes in and we know the characteristics based on the 13 features of the new borrower, can we be able to predict the probability of default for this new borrower? So I maintain the same characteristics for the borrower in assignment 1. So these are the same characteristics you use. You recall in that assignment, we did that for random forest. So for those of you who have not watched my random forest video, you can go to my channel and then watch the random forest video wherein we did the prediction for this same wow. So we come here and then we look at the activation function and the prediction for this new borrower. So I create a frame for the new borrower over here, and these are the characteristics of the new borrower. Then once I create that frame, I want to ensure that this new frame has the same variable name or feature name as my training data set. So that is what I do over here. Then I make sure I scale that these characteristics too, because we scaled our characteristics. So these are the steps. Then after that, I can now predict. And then when I predict, I'm going to predict for each and activation function. So that is what I do. So let's look at, based on each activation function, what will be the probability of default. So good. So what we see over here is, assuming we had decided to use the rectified linear unit, the probability of default would have been 0.3456. And then if we had used the Sigmoid, the probability of default is 0.24. The hyperbolic tangent probability of default is 0.24. And then the exponential linear unit probability of default is 0.21. So what do we see here? What we are seeing here is that if we don't select the best activation function, the probability of default is going to change, and that is definitely going to affect our decision. So we saw that the best model was the Sigmoid activation function. So that means the probability of default of this individual based on the best activation function is 0.2433. It is only close to the hyperbolic tangent. Apart from that, if we select a rectified linear unit, or if we had selected a rectified linear unit, we would have concluded that the individual has a very high probability of default. And by so doing, we would have ended up rejecting this particular individual and not giving the person the loan, which could have been a type 1 error. So thank you very much. This brings us to the end of today's lesson. So we have, in conclusion, we have seen that the activation function affects our outcome in a data set like this.